Stripping down science. The Naked Scientists.
Hello and welcome to this week's edition of The Naked Scientists with me, Chris Smith, with Dave Ansell.
Hi.
And also with Phil Rosenberg.
Hi everybody.
This week it's our Naked Scientist Science Phone-In, and we're answering your science questions. You just send them in by telephone, text or email. Phone in 08459 25 2000. You can text us on 07786 20 1960 or email us on chris@nakedscientist.com.
Also this week we'll be finding out how scientists have come up with a sniffle-free feline for people with cat allergies, how doctors have done the first weightless operation ever, and how an ancient mountain range may have triggered off life as we know it.
Cheers, Dave. Also, we'll be hearing an update on the New Horizons mission, which blasted off early this year to explore Pluto and the mysteries of the outer solar system over 6 billion kilometres from the Sun. Temperatures out there get to a chilly minus 230 degrees C. And mission scientist Hal Weaver from Johns Hopkins University in Maryland, US, will be joining us to tell us live what he expects to find out there.
And if you're in the mood to win something, we've got a fabulous electronics kit to give away tonight. It's been donated by Noisemakers, and Noisemakers are sponsored by the EPSRC, the Engineering and Physical Sciences Research Council. And it's a group of scientists that like to go out and make a noise about science. And they've given us this fantastic electronic experimental kit. You can do over 30 different experiments with it. And if you'd like to have a go at winning it, just have a go at our competition, Science Fact or Science Fiction this evening, or have a stab at this week's teaser, which is, Dave?
What is the smallest bone in the body? So if you want to do that, give us a ring on 0845 25 2000.
The Naked Scientists podcast, powered by UK Fast, the UK's best hosting provider, on the web at ukfast.net.
Now, I don't know if either of you are affected by allergies and allergies to animals at that. Anyone got a cat allergy?
I'm actually horribly allergic to cats. I really struggle. So.
What happens when you get near a cat?
Well, bunged nose, runny nose, eyes streaming, eyes itching. And it sets off a bit of asthma with me as well.
So,
actually.
Phil, would you part with $4,000 to have a cat which wouldn't trigger those symptoms?
If I'm perfectly honest, I don't really like cats, so I probably wouldn't. But my girlfriend actually would be really keen on something like that, because she really does like cats. She's been nagging me for one for ages.
Because researchers for a long time, Phil, have been trying to make an allergy-free, as Dave put it, sniffle-free feline. And we know pretty much which part of a cat it is that drives most people's allergies. It's a certain protein they make. It comes out in their saliva and from their skin. It's made by a gene called FeLD1. And so what researchers over the last few years have been trying to do is to use various genetic tinkering techniques to remove that gene or to substitute an alternative form that doesn't trigger allergies. And there's one particular company in the US, and they're called Allocar, and they were trying to do precisely this, to genetically tinker with a cat to make it so it wouldn't provoke allergies. And when they were doing this, they accidentally came across some naturally occurring cats which had a very different form of this protein that didn't seem to trigger allergies. And so what they've now done is to grow a group of these cats, and they're hoping to start selling them for $4,000 to people
actually
who want
breeding these
allergy-free
cats now.
Yeah, now they did they got somebody to do a simple trial on their behalf to see if the technique would actually work and if the cat genuinely didn't provoke allergies in susceptible people. So they got 10 people who had a proven cat allergy, and they exposed them to their cat called Joshua, which has got this mutated FeLD1 gene. Then they got another normal friendly cat called Tiki, who was a standard normal cat. And then they got a dummy cat that was just a sort of teddy bear.
A stuffed cat to try out.
Got these volunteers and they blindfolded them and then asked them to keep a diary of their symptoms afterwards. And lots and lots of people reported that they didn't have an allergic reaction to Joshua, but they did to Tiki. And so what the scientists are now saying is, well, look, we haven't published the data yet. We haven't actually got proof that if you look in a test tube, you won't find antibodies in patients' blood binding to tissue from these cats, but they damn well work. And they've said, look, if any scientists are sceptical and they have allergies, come and hold one of our cats. And that's Simon Brodie, who actually runs the company.
Oh, well, maybe we'll have to go over there and give them a try.
Now, geologists have been wondering how a whole variety of life appeared on the Earth all at once, because it appears it all suddenly appeared very rapidly in about 575 million years ago. And then again, all the kinds of life which started off as very strange, all sorts of peculiar types of life, and then maybe about 530 million years ago, there's the more normal kind of life which you'd recognise today. And a guy called Rick Squire has been looking at the sediments relating to this period, and it's when Gondwana, or possibly Gondwana land, as Chris is about to tell me, was formed. This was one huge continent which almost all the continents in the world were in one place. And when it was formed, all these it was a huge collision of continents, and it formed in an enormous mountain range. They called it the Transgondwanda Supermountain. It was
How big was it then?
About 1,000 kilometres wide and about 8,000 kilometres long, which is far bigger than the Himalayas are now.
So was this continents pushing together, or were these volcanoes?
Well, it's basically the continents kind of collided together, and if you kind of push two things together, they kind of scrunch up, and so that's basically how all the major mountain
It's a bit like the modern-day Alps.
Yeah, or the Himalayas or any other mountain range. And so you got this huge collision and this massive mountain range. It also happened to be at the equator, so you got lots and lots of rain on top of it and lots of erosion, so you got lots of stuff being swept out to sea. Now, the sea is basically a desert. Most of the sea is a desert because there's no nutrients in it.
It's a very wet desert, Dave.
Very, very, very wet desert, but nothing can grow in it. So without any nutrients, without any phosphorus, without any iron, nothing can grow. So that's why all the fish is found near the edges of the continents.
Yeah.
And so all of a sudden they got all this nutrients, so everything could go really quickly. And so there's all this competition for all this new energy and life. And so maybe this triggered the evolutionary explosion which made life as we know it today.
Phil.
Excellent. Right, OK, I'm going to talk to you now about doctors who have performed the first zero-G operation. Now, it was actually a doctor led by France's chief surgeon, Dominique Martin, and it was backed by the European Space Agency, and it aimed to prove that zero-G was possible in advance of preparations to sort of send, long exploration sort of astronauts into space, maybe to a moon base or something like that. Now, the operation took place on a specially modified Airbus 300 plane, and it actually simulates zero-G by rising and diving at the same speed as someone would fall if you dropped them out of a plane. So essentially, when they're within the plane, they feel as though they're weightless because the plane's dropping at the same speed as they are.
How high do they start on it? Because it's called the Vomit Comet, isn't it?
This is a different one to the Vomit Comet, but yeah, it's the same sort of idea. They start, I'm not quite sure the altitude, but they do drop a long way. They get about 20 seconds of weightlessness every dive that they do. So they fall quite a long way as they're going through
to do an operation, 20 seconds, that's not long to do.
Well, the way they actually did it was that it was quite a simple operation. It was to remove a benign tumour out of somebody's arm. And it was something they could sort of stop and start. And they actually did it in small 20-second bursts. It did about 30 goes at it. So it took them maybe 10 or 15 minutes to do the whole operation.
But what's the point, Phil?
Well, the idea is that they want to look at the possibility of doing this in space for astronauts in space, either in the space station or possibly on the moon. Now, the next step for this whole thing is to actually have a surgeon on the ground and a patient in the Airbus, and a small sort of robo-surgeon that's remote-controlled from the ground by a real surgeon. So then they can sort of see if they can actually do the operation remotely. So you can actually have a surgeon on the ground and an astronaut in space, on the space station, on a moon base, travelling to Mars and some future mission. And actually, if he's got, appendicitis suddenly breaks out, they can have a robot there that can actually take his appendix out with a surgeon on the ground, remote control.
What are the constraints facing people doing surgery in zero-G? Why is that likely to be a problem? Why is it not the same as doing an operation on Earth?
Well, presumably there's certainly some interesting features that can occur with keeping the patient still. This patient actually said that when they went zero-G, it actually floated a few centimetres off the surgery's table. So it was a little bit disconcerting, but they did have a few dry runs to show him what you could expect beforehand. Obviously, I guess there could be issues with bleeding and losing blood into the cabin and that sort of thing. And again, this was quite a simple operation with minimal bleeding, so that was all kept under control.
You're listening to The Naked Scientist with Chris, Dave and Phil. Don't forget our teaser this evening, and up for grabs is a fantastic electronic kit which has been donated by the guys at noisemakers.org.uk. We want to know what's the smallest bone in the body, and if you can tell us not just its name but where it is, then we'll give you a bonus mark. The phone number 08459 25 2000. You can email chris@nakedscientist.com or text in on 07786 20 1960.
Sorry. Now, scientists have got worrying news for anyone who uses a GPS navigation system, because in 2011 you might find it suddenly not working. Because the sun has an 11-year cycle. Every 11 years you suddenly get lots and lots of explosions on it, huge things called solar flares, which fire out lots of charged particles which crash into the Earth's magnetic field and produce lots of interference, lots of radio noise.
How does that work? Why do they do that?
Well, basically, if you slow down something charged very quickly, it will produce a radio wave. That's actually how a radio transmitter works. It makes electrons fly up and down inside an aerial, which produces radio waves, and that's how you can hear a radio. Now, the problem is that this radio noise, is actually concentrated at the same frequencies, about 1.2 to 1.6 gigahertz, as a GPS system, which is somewhat unfortunate because all of a sudden the signal is going to get about 10 times weaker. Which,
But could we have predicted that the sun was going to do this? Presumably we could. And would we have been able to predict, theoretically, that when that solar radiation hit the Earth's magnetic field, it was going to make interference of that frequency? And therefore, could we have worked around this?
I guess people could have predicted it, because it hasn't worked, because a guy from Cornell University called Alessandro Cerulli actually discovered that this, when he was playing with the GPS system, it suddenly stopped working, and he correlated it with a solar flare. And so they could have worked around it by producing basically more powerful transmitters, basically shout over all the noise. But that's going to involve rebuilding all the satellites and sending up new satellites.
So is that what they're advocating? What are we going to do to get around this?
Whether they'll be able to do it in 5 years is probably debatable, because building satellites takes a long time. I'm sure Phil will know.
Absolutely, it's going to be one of those things that's going to take a lot of money, I'm sure, and a lot of time to get sorted out.
It's quite fun. You can download different voices to have on your GPS to guide you, can't you? And one of the ones on offer, someone suggested Tony Blair. But that's a bit of a worry, because no one would believe a word it said. You'd all be going wrong anyway, wouldn't you?
The Naked Scientists. Supported by the Wellcome Trust.
Now it's time for a bit of kitchen science. And this week, Derek's with a whole host of people at Norwich School: Hugh Hunt, Matt, Tom and Pete, and they're waiting to find out about the science behind hurling your homework into the air. Hi, Derek.
Hello there. Welcome to Norwich School, where we've come today to do some very easy science experiments, which are actually, they hardly need anything, and I'm sure everyone listening to this at home can do it. So I hope you can listen up and listen out for what you need to do. With me is a new recruit to the Naked Scientist, who's going to be doing some experiments for us here on the show. So I wonder if you could just tell us who you are and quickly and where you're from.
Yeah, I'm Hugh Hunt, and I'm from the engineering department of Cambridge University.
OK, well, thank you very much for, coming along and setting up the experiment today. And so, what is it we're going to be doing today, very quickly?
Well, we're going to see what happens when you toss your mobile phone up in the air.
And also with us, we've got 3 helpers from Norwich School to kind of do the experiment and to tell us what's happening. So I wonder if you guys could, in turn, tell me your names and what years you're in, please.
Hi, I'm Matt, and I'm in Year 10.
I'm Tom, and I'm also in Year 10.
I'm Pete, and I'm also in Year 10.
OK, 3 guys in Year 10. So quickly then, I've got to ask you guys what you like about science and see if we can satisfy your science needs today. So, Matt, what do you like about science?
I'm just really interested in how the universe works and what makes it up.
All right, and I think we'll be exploring a little bit of how the universe works today, hopefully. And Tom, what about you?
I enjoy seeing interesting reactions between chemicals and such like.
OK, good stuff. And finally, Pete?
I like the way it affects the world around us and everything in it.
OK, good. And something we always do is explain how our experiments kind of relate to the world around us. So we'll be doing that later on. Now then, Hugh, we're here armed with nothing other than a book, basically, and that's all you need at home. And this book actually has to be rectangular in some way. So if there's a square book, then that won't actually do. And also, it's good to make sure that the leaves and the pages of the book don't come apart, because we're going to be throwing this thing in the air. So a rubber band just to kind of put round the book is very good, just to keep all the pages in place. OK, so there we go. We are armed with a book. Quickly, what's this wonderful tome we have here?
Well, this book happens to be called Machines in Motion.
Absolutely, and it looks fascinating, and we are going to be putting it in motion. So, Hugh, why don't you instruct Matt, Tom and Pete what they've got to do with this book?
Yes, well, look, what we're going to do is we're going to ask each of you in turn to spin the book in a different way. Now, the first way we're going to spin the book is we're going to put the book down on the table in front of us with the spine pointing away from us. So I have to turn my head sideways to read Machines in Motion. So, Matt, what I'd like you to do is to pick up the book and then to spin it and just see what happens.
Well caught. What happened there?
The book has just landed right in my hand in exactly the same position as I threw it up from.
OK, yeah, no, he's absolutely right. Is that right, Hugh?
Yeah, well, in fact, nothing particularly remarkable happens. It spins as you might expect it to spin.
Exactly, so that wasn't so exciting. Things do get better, though. OK, so, Tom, what would you like him to do?
Right, well, now, what we're going to do is we'll stand the book up with the spine still facing away from us, but we're actually going to spin it in the vertical plane, as it were. So the book is going to be spinning about its thin direction.
Exactly. So the book is actually standing upright on the table now, and as Tom is looking at it, he can't actually see the cover of the book. All he can see is the thin end of the book. And Tom, you're going to you pick it up and kind of spin it towards and away from you. And tell us what happened.
OK, that spins about the same axis all the way through, so nothing changes really as it moves.
OK, then. So there we go. That was all pretty expected, wasn't it, Hugh? So finally, then, what do we have to do?
We're going to put the book on the table in exactly the way you would as if you were about to read it. And Pete's going to try and give that a toss and catch it.
OK, but we are not going to do this just yet. Pete is itching to do it because he's told us he's a cricket player, apparently, so he knows what he's doing when he's catching stuff. But we are asking you guys at home to do this first and tell us what happens. So if you get the right result, then you can win a prize from us too. So the number is 08459 25 2000, and you can also email chris@thenakedscientist.com. Now, before we go back to the studio, I'd just like to ask Pete what he thinks is going to happen when he throws that book up. What do you think is going to happen there?
I think it's either going to spin fairly evenly, as in the previous two experiments, or it's going to spin fairly unevenly, as the weight isn't evenly distributed throughout the book.
Sounds good, although I think he's covered most bases there. I think one of those probably will be correct, but we're going to find out which. So there we go. Anyway, we're already here at Norwich School, so we'll be coming back later in the show to find out what happens. So until then, it's back to the studio.
Thanks very much, Derek, and there'll be more from that later on. And just in case you missed how to do it, all you need to get hold of is a rectangular book. It needs to be hardback, really. Put an elastic band round it, hold it on the bottom two corners as though you're about to read the title, throw it up in the air, make it spin, and then watch what happens as you catch it. What happens? If you think you've done this correctly, phone in now on 08459 25 2000, or you can email chris@nakedscientist.com or text in on 07786 20 1960.
Also, for anyone who wants to have a go at our teaser tonight, the question is, what is the smallest bone in the body? And also try and guess where it is. The number to call in, if you've got the answer, is 08459 25 2000.
And so far, Ben in Mildenhall, Rowena in Malden, Lorraine in Papworth and Betty in Northants have all got it right, so well done you.
Okay, I've got a question here which is coming from D. Shard, who says, can you please tell me how to stop my body making mucus? I have dysfunctional eustachian tubes for 7 months, and although they're sometimes on the point of clearing, then along comes more mucus and the whole thing starts again. I've been prescribed some nasal spray, but it's really depressing not being able to hear people talking to me clearly. But why do we need mucus in the first place, Dave?
Well, it's very important for you, especially in your lungs. We did an experiment with this on TV a while ago. Basically, what it does is it catches all the dust and stuff. So when you breathe in, if you didn't have any mucus, it would get all the tiny bits of dust deep into your lungs. They can do all sorts of damage, especially if they're toxic. And so the mucus is just being sticky. It tends to just catch them, and then you bring it up again as phlegm, or it runs out of your nose, and it takes away all the poisonous, nasty stuff, basically.
So I guess that the reason that this person's got chronically mucousy airways is probably because of some kind of allergy. We were talking about allergies earlier. It could be an allergy. It could also be some kind of other inflammatory process going on. But usually it's down to something in the air that you're breathing in that's making your airways inflamed. And the reaction to an inflammation is to make lots of mucus. How do you get rid of it? Well, there's one way to knock it down, which is to do what you've done, which is take some steroids, a nose spray that squirts a small amount of steroid into the nose. That will help to stop the inflammation quite effectively. The other way is you can take some antihistamines and things like Piriton, which you can buy over the counter. Pretty good, because they stop histamine, which is made by a class of cells called mast cells. And mast cells are coated in an antibody called IgE that recognises allergy-provoking substances. And when the allergy-provoking substance binds onto the antibody, the IgE on the mast cell, it tells the mast cell, pump out this histamine, which is the inflammatory substance that makes you then have sticky eyes, itchy eyes, runny nose and blocked up nose. So if you take some antihistamines, you can block the action of the histamine before it actually has a chance to get going.
That's actually exactly what I do for my cat allergy, so there we go.
Is it? OK, well look, here's Andrew. He's on the line in Essex. Hi, Andrew.
Hello.
Welcome to The Naked Scientist. What do you want to talk about?
Magnets.
OK, what's your question?
What are magnets made out of, and why are they made?
Well, magnets are very useful things. I mean, but you've probably seen them. You can stick things to fridges with them, and they're very important in things like hard disk drives in your computer. They're used all over the place. They even make levitating trains with them. They've got a levitating train in China now, which works like this, going between Shanghai and Shanghai Airport.
Didn't we have one in this country that broke down?
Yeah, various people have built them in various places, and very few of them they've been too expensive to build. But anyway, how you make a magnet? Basically, inside something like iron, there's lots and lots of all the little atoms are actually magnets themselves. But to start off with, they're all pointing in different directions. It's like if you throw a big bucket of magnets if you had lots of magnets in a big bucket, they'll all be pointing in different directions. And so what you need to do to make it what you'd see as a magnet, so that some of the magnetism can get out, is you need to line up all those magnets. The way you do it is you heat up the material, which lets all the magnets start to move around. If you get it above, with iron, about sort of 300 or 400 degrees centigrade, maybe 5 or 6, you heat it up, then you put a big magnetic field on it with maybe some some wires and some coils. This big magnetic field causes all the little magnets to line up, like you may have seen compasses do in a magnetic field. And if you cool it down in that magnetic field, they'll all be lined up, and you'll have what you think of as a magnet.
But David, what about other substances? Because it's not just iron that's magnetic, is it?
Of the elements, it's iron, nickel and cobalt, but you can get all sorts of strange alloys of things which can produce stronger magnets, because to make a very, very strong magnet you need something which will, once you've aligned all of the little tiny magnets, they need to stay there, and it's very difficult to make a very, very strong magnet and make them stay there, because they all want to line up and point towards each other again.
Why can't I, say, magnetise my gold wedding ring?
Only iron, nickel and cobalt will produce very strong magnets, whereby actually the little magnets tend to like lining up next to each other, all in the same direction. With things like gold, I think possibly gold's paramagnetic, they will line up if you apply a magnetic field, but they won't line up of their own accord, so it's much, much weaker.
Does that help you out, Andrew?
Yeah.
Have you got a magnet?
Yeah.
Have you ever made an electromagnet?
No.
That's quite exciting. If you can get a big bolt or something made of iron, get a piece of wire and wrap it round and round and round and round and round and round and round, round lots and lots and lots of times, and then connect a battery to each end of the wire, you'll find that you've made a magnet, because when the current passes through the wire, then it induces the magnetic effect that Dave was talking about in the iron of the bolt, and you make a new magnet. How's that?
All
Be careful, it can get very hot, though, if you're not careful.
It can do. Now, do you want a quick go at the quiz, Andrew?
Yeah.
OK, here we go then. The Big Bang, which gave birth to our universe, occurred 15 billion years ago. Is that science fact or science fiction? What do you think?
Science fact.
That's absolutely true. If you actually look at the universe, you can actually wind back the clock looking at all the different galaxies out there, and we found that the universe is about 14 or 15 billion years old.
Well done, 1 out of 1. Brilliant. Very hard question coming up, though. The average human contains about 1 million red blood cells. Do you think that's fact or fiction?
Fact.
I'm afraid not. It's far, far more than that. You get about 30 million red blood cells inside your body, all carrying oxygen around your body.
But Andrew, it was a brilliant question, so I'll tell you what I'll do. I'll give you a special copy, signed by me, of my book, Naked Science, for being such a great guest. So thanks for joining us on The Naked Scientist, 1 out of 2, and you're in the hat and in the lead at the moment. Right, let's have a quick chat to Connor. Hi, Connor.
Oh, hello.
Thanks for joining us on the show. What would you like to talk about?
Yes, could you tell me if the ozone hole is now getting smaller since CFCs have been banned?
Well, it's not actually got any smaller yet, but it's stopped getting any bigger.
Oh.
Which kind of amounts to the same thing, because, of course, what we see is a lag between the CFCs, the chlorofluorocarbons, which are implicated in causing the ozone hole, going into the atmosphere. Then they react over Antarctica and damage ozone and make the hole bigger. But if you're seeing the hole not getting any bigger, then that means that the reaction that's causing it must be slowing down, and at the same time ozone's continuously being remade, so the two processes must now be in balance, which suggests that if it keeps on slowing down, within the next few years the hole should begin to shrink a little bit. But let's not be too overconfident or complacent about this, because the ozone hole is actually the size of the whole of the North American continent. It's huge. It's the size of Australia, the hole we've made.
Right. Have all CFCs been banned, do you know?
Well, people have made a profound effort to try to stop doing this, but the thing is there are still some which are in use which we can't really find an alternative for. If you go and have an operation in hospital, for example, a general anaesthetic often involves using CFCs, and these not just to make them actually volatilise, the actual anaesthetic agent is itself a kind of CFC. It's an organic molecule, so a hydrocarbon-type molecule, but with lots of these chlorines or fluorines linked onto it, and they work very well as general anaesthetics, but unfortunately they're not too good when you mix them with ozone.
Oh, so we should stay healthy then?
Well, you might stay sleepy, the more of them we make. But no, on the whole, the Montreal Treaty in the late 80s, I think 1986, said that we shouldn't be using these things anymore, certainly not in the volumes that we were, and they started to find safer and cheaper substitutes. Right. And as a result, we've stopped pumping them into the air, but the problem is they're very long-lived, which means that once they're in the atmosphere, they eventually make their way down to the South Pole, and that's because the Antarctic circulation, the air over Antarctica, works a bit like a giant whirlpool, and it sucks in contents and constituents of the atmosphere and concentrates them there over winter time. So when the sun starts shining in the springtime over Antarctica, which is coming up soon, then what's actually going to happen is that you get a reaction involving light and the fluorocarbons, and they then start to break down the ozone. And so all the time we're going to see a bit of a lag. So perhaps 50 years from now we might see the whole getting better.
Oh, right. Okay.
Quick go at the quiz.
Yes, please, yes.
It takes about 8 minutes for radio waves to travel from Earth to Jupiter. Do you think that's science fact or science fiction?
Fiction. I think is it to the sun it's 8 minutes.
It is true.
Yeah.
If you work it all out with the speed of light and the distance to Jupiter, you actually find that it will take 2,000 seconds, or about 37 minutes to arrive.
Right, no, okay.
And the surface of the sun is about 10,000 degrees Celsius, Connor. Fact or fiction?
Yes.
I'm afraid it's not. The actual surface of the sun is only about 6,000 degrees centigrade.
All right.
Only. Thanks for joining us on the show, Con. It's great to have your company.
Bye-bye.
The Naked Scientists, Chris, Phil and Dave. And this evening we're doing a Naked Scientist Science Phone-In, an hour of your science questions on any subject. You just have to call in and we'll tackle your questions. 08459 25 2000 is our number. You can text in on 07786 20 1960 or email chris@nakedscientist.com. Here's a quick one for you, Dave. This is an email. It's from Esther, and she says, I know cassette tapes are practically obsolete, what with CDs and MP3 players, etc., but I have a question regarding them. Very often, when I'm listening to my Harry Potter audiobooks, there's a muffling in the background, and if I listen very carefully, I can hear the other side of the cassette being played. I've tried this out with several different types of cassettes and with different players. Is there a scientific reason behind this, or is my brain just going mad?
Well, the way a cassette tape works in the first place is you have a big long strip of actually a kind of iron, and when you apply a magnetic field to it, it gets magnetised. And that's how you record things onto it. And you get a varying magnetisation, and then you turn that into sound, vibrations, and you hear that as sound. Now, the way that a double-sided cassette tape works is when it's one way up, it reads the information off the bottom of the cassette, and then when you turn it over, it'll read it off the top of the cassette. So you get two strips, one at the top and one at the bottom, with different information on it. So what's probably happening when you're hearing the muffled thing is maybe the sensor, which is measuring the magnetic field, is a bit too close to the middle, and so you're picking up some of the other side of the tape, probably backwards, as you listen to your side of the tape. And I think that's what's happening.
Do you want to have a go at our teaser this evening? We want to know, and this is to win an electronics experiment lab that'll let you do 30 different funky electrical experiments. We want to know what's the smallest bone in the body, and for a bonus, can you tell us where it is? If you think you know the answer, 08459 25 2000, email chris@nakedscientist.com or text in on 07786 20 1960.
And now we're going to hop over the ocean for this week's Science Update, where Bob and Chelsea discuss how killer whales kiss and make up after a dispute, and how scientists are making strides towards developing artificial gecko feet.
This week on Science Update, we'll learn why top engineers are working long hours studying lizard toes. But first, if fighting and making up with your significant other sometimes feels like a highly choreographed dance, you'll probably identify with this report from Chelsea.
At least one killer whale couple has a way to kiss and make up, and others may too. That's according to animal behaviorist Michael Noonan of Canisius College and his student Serene Giordano. They studied a year's worth of videotape of one pair of captive killer whales and found 8 incidents of aggression in which the female chases the male. After a cooling off period, Noonan says the killer whales then begin to swim along side by side in a behavior called echelon swimming.
So their eye patches match, and their tail strokes stroke in synchrony. So they're swimming in it almost looks like a dance. It almost looks like an underwater dance. It's beautiful to watch.
He says echelon swimming is a common behavior among other captive and wild killer whales, and scientists believe it reinforces bonds between animals. He says only more research can show whether other whales use echelon swimming to make up after quarrels, but it's intriguing that the animals seem to have the capacity for reconciliation at all.
It's hard to name something that's more valuable in human behavior than peacemaking. So it's particularly exciting to see the suggestions of peacemaking in killer whales.
He adds that it's one of only a few known peacemaking behaviors outside the world of primates.
Thanks, Chelsea. Well, here in the States, a cartoon gecko is a well-known spokes animal for a car insurance company. But selling insurance isn't their only trick. Geckos are also marvels of engineering. That's because the surface of their toes is packed with millions of tiny spatula-shaped hairs. These hairs create enough friction to allow the gecko to scamper effortlessly up smooth walls and enough adhesion to hang its entire body weight from a single toe. And yet the hairs can release their grip just as quickly and easily as they stick. And that's why electrical engineer and computer scientist Ron Fearing of the University of California at Berkeley is leading an effort to create artificial microfibers that act like gecko feet. Their current prototype packs 250 million hairs per square inch.
These hairs make intimate contact with glass, and they don't slip. It's very, very high friction. But it doesn't quite work like the gecko, because if you try to pull it off, it just pulls off really, really easily, actually much easier than the gecko pulls off. So we'd say we're about halfway there in terms of building a structure that mimics the key aspects of gecko hairs and gecko feet.
He says their current material could provide good traction for tires and shoes, but the technology could also lead to other applications, from pain-free adhesive bandages to wall-climbing robots.
Thanks, Bob. That's all for this week. Next week, we'll discuss some more cutting-edge technologies, one that should prevent train derailments and another that should speed up biohazard detection. Until then, I'm Chelsea Wald.
And I'm Bob Hirschon for AAAS, the Science Society. Back to you, Naked Scientists.
Thanks, guys. Chelsea and Bob there at Science Update, and you can find out more about that at scienceupdate.com if you want to go and check out their website and find out a bit more about what's going on the other side of the Atlantic.
And if you want to have a go at our teaser question, all you got to do is phone in and answer, what is the smallest bone in the body?
We've got a few answers in here. We're looking at Keith, you look like you've got it right, and Gladys. Ben in Mildenhall, unfortunately, not looking so good, and Betty in Northampton, have another go.
Laying the facts bare, the Naked Scientists.
Now, one thing I flagged up earlier was that we're going to be joined this evening by Hal Weaver, who's from the New Horizons mission, and he's joining us right now from Johns Hopkins over in the States. Good evening, and in fact, good afternoon for you, Hal.
Hi, how are you?
Very well, thank you. Thank you for joining us. Now, why are you going to Pluto? What's the point of this?
Oh, it's been dramatic, the change in our perspective of what the solar system is over the past 10 years, and Pluto's been at the forefront of that new understanding. Pluto is there's a big controversy about whether or not Pluto is a planet, but it's definitely something called a Kuiper Belt object. This is a new region just outside Neptune's orbit, just discovered in 1992. We now know of over roughly 1,000 objects out there, a whole new region of the solar system that hasn't been explored yet, a region that we're calling the realm of the icy dwarfs, and Pluto is the prototype of those objects.
So what do we think's out there, Hal? What are these objects actually like, and why are they worth studying?
Yeah, well, they're worth studying for a couple of reasons. One is that because they are so far away from the Sun, they're outside of Neptune's orbit most of the time, they've always been cold since the time that they formed roughly 4.6 billion years ago. And as you know, one of the best ways to preserve material is to keep it in a deep freeze. And that's exactly what's been done with these objects. They have a lot of ice, and the molecules that they have retained over these last 4.6 billion years basically gives us a window back to the time of the formation of the solar system. So by studying these objects now, we have a much better insight into what was happening in the early solar system in that region of the solar system compared to observing, like, for example, on the Earth or other planets where there's been, these objects have had so much evolution over the age of the solar system.
How long is it going to take New Horizons to get to Pluto? Because it left in, February of this year, wasn't it?
It was January the 19th of this year that we took off, and we went screaming off of the surface of the Earth, the fastest spacecraft ever launched, going at about 36,000 miles per hour. But even going at those kinds of speeds, it's still going to take 9.5 years to get to Pluto because Pluto is so far away. It's roughly 30 times farther from the Sun than the Earth is. And so even though we had the most powerful rocket available and had a very, very favorable launch, and we're heading, first of all, towards Jupiter, and one of the big reasons for going by Jupiter is to get a gravity assist. We're going to get like a little slingshot effect because Jupiter is so massive. Of course, it's by far the largest planet in the solar system. It has a mass of about 320 times the mass of the Earth. the most important objective of our Jupiter encounter is to hit a little keyhole in space, a little spot near Jupiter that will propel us on towards Pluto and cut about 3 to 5 years off of our travel time. It increases our speed by about 20%. But still, it is going to take about 9.5 years to get to Pluto. But we know now that we'll arrive there on July the 14th of 2014.
How do you actually know that the probe's going to, A, survive the journey and B, be able to operate under those extremes of temperature? Because it must be about, minus 200 degrees Celsius out there near Pluto. How's it going to operate?
Yeah, that's exactly right. There's very harsh conditions out there. But our spacecraft will actually be nice and toasty because we have, it's almost like a thermos bottle. We have this multi-layer insulation wrapped around the entire spacecraft. And just from the heat generated by the electronics, we generate enough heat to keep all of the instruments, the spacecraft body and the telescopes and so forth, at roughly room temperature, even when they're out at Pluto. So, for most of these instruments.
So what sort of science will you be doing when you're at Pluto? In what way will you be interrogating that bit of the solar system with the probe?
Yeah, there's just some very basic questions that we want to address that are just too hard to do remotely, because we are so far away from Pluto. First of all, we just want to see what does it look like in detail. Even, Hubble Space Telescope, the most fantastic observatory available to us here on Earth, can barely resolve Pluto. It's done some magnificent imaging of Pluto, but even with Hubble, it just looks like a bunch of, maybe 10 pixels across, something like that. You can't really, all you can tell is that there are some very bright regions, some very dark regions, but it's very hard to tell exactly what's going on. Why are these regions bright? Why are they dark? And to get any kind of detail whatsoever. We'll do thousands of times better than that by flying a spacecraft by. And
when you're out there, how long will it take a message or any of this data that you're collecting to get back to Earth each time?
Yeah, it's amazing. I heard that little spot you had on a few minutes ago about how long it takes to go from Jupiter. Well, from Pluto, you turn on a flashlight at Pluto, it takes 4.5 hours for the light to reach the Earth. So the round-trip light time is about 9 hours.
So it's a long old time. Once you've got to Pluto, will you carry on and actually go beyond the orbit of Pluto and keep exploring?
Well, that's exactly right. That's what we're hoping to do, is not to stop at Pluto, but to continue plunge. The spacecraft will continue to plunge deeper into this region called the Kuiper Belt. And as long as everything is still working then, we have a very good chance, we estimate on the order of 95% probability that we'll be able to encounter another small Kuiper Belt object, at least one and maybe two. But, even, with Pluto, the funny thing is we just discovered about a year and a half ago 2 more satellites that Pluto has. Besides Charon, the one that was discovered in 1978, we have 2 more little satellites. We have our own little mini solar system out at Pluto. So effectively, we have 4 Kuiper Belt objects to look at for the price of 1 by going by Pluto. And that is the prototype of these Kuiper Belt objects. But we, in fact, do hope to, you get the neat thing is that we have sort of one of the largest members of that class, and the smallest satellites in that system are among the smaller objects in that class. And then plus, we hope to encounter at least 1 or more of the small Kuiper Belt objects to see whether or not they're, like the objects in the Pluto system are very different.
Thanks very much, Hal. That's Hal Weaver, who's one of the scientists on the New Horizons mission, which is the fastest space probe ever built and launched, and as he said, won't be there for quite some time yet, but obviously is just in the realms of Jupiter now and beginning to send back some absolutely fantastic pictures. Thank you to Hal Weaver from Johns Hopkins University. Fiona's on the line. Hello, Fiona.
Hello.
Thank you for joining us on The Naked Scientist. What would you like to talk about?
Okay. I'd just like to ask the question, why is blood the colour red? Why is it red?
Well, Fiona, the reason it's red is because, as you probably guessed from being told to eat lots of iron, which makes you have nice rosy cheeks, blood is red because it's got iron in it. Now, if you look down a microscope at blood, what you'll see are thousands of tiny little red cells that look like what are referred to as biconcave discs. If you look at them from the side, they're the shape of a number 8, and that's because they've got a thick ring around the edge and a flattened centre, a bit like a donut, really. They're crammed with a substance called hemoglobin, and hemoglobin is the stuff that carries oxygen around the body. It's a protein. In fact, it's 4 proteins stuck together, and in the centre of those 4 proteins, in the ring in the middle, there is an iron iron. So there's some Fe for iron. And because it's got iron in there, it has the colour red. Now, lots of animals have a different version of that protein. They have their own version. So, for instance, a horseshoe crab, which you might have seen if you watched David Attenborough, these amazing creatures, actually, they have blue blood because they don't use iron. They have a different metal in there. They have copper. And the real hippies of the haemoglobin world are a kind of worm. There's a sort of annelid worm that lives in the sea, and it actually has blood which is purple when it's oxygenated, and it goes a colourless or a non-purpley colour when you take the oxygen out of it. So, all very exciting.
Thank you.
That's all right. Do you want to have a go at our quiz?
I haven't really got time, I'm sorry.
That's all right. But thank you for joining us anyway. It was a lovely question.
Okay, thank you.
Thank you.
Bye-bye.
Now, we've got some more questions, have we, guys?
We have indeed. Now, let's go first over to Matthias. He says... Oh, no, my apologies, I've got the wrong one. Here's one from Jordan in the US. Now, he wants to know, can he have a leech for a pet? Is he allowed to buy one? If so, where can he buy one?
Dave, do you have any leeches going?
I haven't got any at home. I've picked some up by wading in streams occasionally. I guess that's the easiest way to find one. Just kind of wade around and they'll find you.
Because medical companies do actually supply them, don't they?
Yes.
Because you can actually buy leeches for medical purposes, because when you, for instance, I mean, in the old days we used to bloodlet people because people thought it was good to leech blood away from people. But in fact they're very, very useful leeches because they have a venom which stops blood clotting. It's called hiruridin. And it's a tiny protein. When they bite you, they inject it, and it keeps the blood from clotting so they can keep drinking. But why surgeons love them is because if you have a bit of plastic surgery, part of your body is severed and has to be reattached, like a finger or part of your ear, it's very easy to reattach the blood vessels like arteries, for example, because they're quite large and chunky and you can spot them. The tiny artery is really easy to reanastomose, really. But the veins are quite floppy, and they're actually quite difficult to identify, and it's very difficult to reconnect them. So blood can get into your tissue quite easily, but not back out again. And what this can do is to cause a sort of traffic jam, and blood can get in but not out, and so the tissue actually ends up starving because it doesn't get enough blood.
Circulation going all the way through.
That's right. So what scientists and doctors have found is if they attach leeches around the site where you're trying to stitch something back together, you can keep pulling the blood out, and as long as you keep a nice flow of blood coming in, then the tissue sort of revitalises, and then those blood vessels grow back together.
So the leech is almost sucking the blood actually through the finger or something?
Exactly that, yeah. And then when the leech gets full, it just drops off. And there are companies, I think there's a company in North Wales that will supply medicinal leeches, but usually they're used by doctors rather than just members of the general public. But as Dave says, you just get them from streams and ponds. I found them in streams and ponds locally. I haven't tried attaching them to myself yet. It'd be quite interesting, wouldn't it, try that?
I guess there's a limit to how many you want, to how big a part of the body you can use like this, because you'd run out of blood fairly quickly. Now, here's another question for you, Chris. Here's one from Kane Cock, and he says, "Hi, Chris. Is it true that some of our senses degenerate and some are more susceptible to damage than others? We see kids wearing glasses and we don't need hearing aids until the point we're really old. What's going on?"
I think with glasses, there's definitely an environmental effect there, isn't there? Because if you spend all your life studying, then you're much more likely to end up with short-sightedness. I mean, I noticed that me and Phil have both got glasses on today.
Absolutely.
But in Singapore, where there's a very strong emphasis on education from a very early age, and lots of people spend a lot of time studying, the rates of short-sightedness have gone through the roof. And there's a lot to be said for people going out on the sports field and learning to focus their vision in the distance, because I think when you're young and your body is developing and growing, then if you do a lot of close work, you don't develop the capacity necessarily, if you're prone to developing short sight, to see well into the distance. You tend to accommodate much more closely. So I think there's a lot to be said for actually doing a lot of distance work. But in terms of actually degeneration, just because you need glasses, it doesn't mean that your eyes are actually degenerating. It just means they're not working as effectively as they could. But if you put glasses on, they still give you crystal clear vision. Going deaf, on the other hand, there's actually a problem with the part of the ear that turns sound waves into electrical signals. And that's because over time, the tiny nerve cells that do that job get damaged by loud noises. They also get damaged by the effects of ageing and the effects of damaging chemicals in the bloodstream. And once they're lost, then you can't actually replace them. And that's why you do develop progressive deafness.
Does you ever lose your sense of touch with age or with time?
People do report that they get slightly less acute touch, but not in quite the same way and quite the same dramatic way as if you were to work in a very loud environment, such as if you play woodwind in the orchestra and you've got the trumpet playing right behind you in your ears, or you work in the old days in a mill where it was very, very loud, and chronic exposure to very loud sounds is known to damage hearing.
I have heard of a case where someone actually had lost their taste, with age, and actually this poor gentleman actually died because he actually accidentally ate a daffodil bulb instead of an onion. And daffodil bulbs are actually quite poisonous, so make sure you don't do that at home.
Well, daffodils have actually got a stuff in them called galantamine, which is one of the drugs which is being trialled as an anti-Alzheimer's agent because it can push up the level of a nerve signalling compound called acetylcholine in the brain that's lost in people who have Alzheimer's. Here's a question for you two. Look, this is from Clementine in Cambridge, and she says, who would win a fight between a hippo and a polar bear?
Well, I think that polar bears are a lot faster than hippos, so I think that element of nimbleness would give it a big advantage.
Although I guess if they got close enough, a hippo is a really vicious animal. I think more people are killed by hippos in Africa than they are by lions and tigers and actual carnivores.
Now, if you're at all arachnophobic, in other words, you hate spiders, cover your ears, because Adam Summers is from the University of California in Irvine in the US, and he's got a very sticky story for us about big spiders, or tarantulas.
We've found that tarantula spiders, at least one species of them, produces silk with their toes. So they actually are producing the same sort of silk that spiders produce to make webs, except that instead of producing it out of their spinnerets, which are on the back end of the animal, what's called the epithysoma, or the abdomen, they're producing it out of those 8 little legs that are up on the front end. And, of course, they're tarantula spiders, so there's nothing really little about them.
But why would they want to do that? Why do they need the silk to come out of their feet?
Tarantula spiders are terrestrial. They run around on the ground, and we suspect that this silk is used to increase both friction and adhesion with their toes. Spiders have a really well-known dry adhesive system that's quite similar to the gecko toe, but that doesn't always work, and so having some sticky silk that comes out can give them a little more traction. And remember, these are great big spiders, and they don't have a very well-armored exoskeleton. So if they fall, they're in real trouble.
So that the theory would be that they, first of all, glue themselves to a surface, and then as they move along, they're laying down a line that can essentially be a prevention to stop them falling.
Well, no, not quite. So what you've just done is given a very nice description of what's called dragline silk. And most true spiders will lay down a dragline. Every step they take, they glue down a little bit of silk behind them, and if you knock them off a table or something, they'll just hang by this thread. That's not what's going on here. These threads are unbelievably short. It was only through basically happenstance that we managed to visualize them at all. They are on the order of 1 or 2 millimeters long coming out of the foot. And so they're really only visible if you're looking at the footprint that's been left behind in the event that the spider skids its foot a little bit.
Is that what you did to see them?
Well, we had a very lucky thing happen. One of the authors on the paper was in charge of getting spiders to walk on glass, and we were then going to look at the footprints. And one day he sort of took a longer break than usual and left the spiders on a tilted piece of glass. And when he came back, these spiders, which don't like to climb on tilted glass, and so they sort of freeze and don't move, the spider had slipped backwards. And as it slipped backwards, you could actually see this little bit of silk at the end of each foot. And once we'd seen that silk, we knew how to get it and how to visualize it, and so we were able to see it when they were walking normally and able to put it under the scanning electron microscope and visualize exactly what the fibers themselves looked like, as well as subject them to some chemical tests and sort of see that they are just as difficult to dissolve as regular spider silk.
So what came first, actually the ability to spin silk from the abdomen or the ability to spin silk from the feet from an evolutionary point of view?
Therein lies the really interesting question. And Cheryl Hayashi, who's at the University of California at Riverside and is a co-author on this paper, she uses genetic techniques to try to understand which of 2 scenarios happened. The spinnerets, which make silk in all spiders, are thought to be vestigial limbs. Did those limbs have silk because all arthropod limbs have silk? Or did the limbs gain the ability to produce silk because the hardware for producing it was already in the genome and it was being expressed in the spinnerets?
That was UC Irvine's Adam Summers describing the discovery of tarantula spiders making silk from the tips of their toes. And there are more interesting stories like that every week on Nature's podcast, which is freely available from nature.com/nature/podcast.
Sorting out the sparks from the quarks. The Naked Scientists. For more information, get online at nakedscientists.com.
It is The Naked Scientists with Dave, Phil and Chris, and we're taking your science questions this evening. But also, it's your opportunity to win yourself a fantastic electronic project kit from Noisemakers. They're the guys that are a bunch of scientists that want to get science out there for the general public, and you can find out more about them at noisemakers.org.uk.
To win that, all you've got to do is answer a simple question. What is the smallest bone in the human body? And for a bonus, whereabouts is it?
Now, we asked you this evening if you could tell us on Kitchen Science what would happen if you got a rectangular book like a hardback with an elastic band around it, held it on the bottom two corners as though you were going to read the title, and then threw it up in the air to make it spin, and then what happens as you caught it? Well, Amy's had a go and she joins us now. Hello, Amy.
Hi.
What happened when you did it?
Well, I threw it into the air and it sort of flipped over in the air and it was like spinning on its spine axis.
Very interesting. Shall we find out if you're right?
Yeah.
You stay there. Let's go back to Derek, who's at the school in Norwich, and we'll find out if you're right. Derek.
Hello there. Welcome back to Norwich School, where we've got the book right in front of us called Machines in Motion, which is very soon going to be thrown in the air by Pete. Matt and Tom are also standing by, ready to kind of observe what happens to the book. And, of course, remember that we've put the book in the kind of position as if you were about to read it. So there you go. It's flat like that, and Pete's about to spin it. So, Hugh, why don't you just finally instruct Pete what to do?
Yeah, well, Pete, just imagine that you were going to hold the book at the bottom two corners, and you're going to toss it up in the air, make it spin, and then try and catch it, OK?
OK, so what happened that time, Pete?
It landed pretty much exactly the same way up as I threw it, but rotated around 180 degrees.
OK, yeah, so the front cover was still facing upwards, but this time the title was actually upside down, yeah. And Matt and Tom were also kind of watching the spinning there. So, Matt, what did you notice about kind of the way that the book span? How do you think it span?
I noticed to start with it span normally, but as it got to the top, it then rotated a different way so that it would land upside down.
OK, Tom, any thoughts on that?
Yeah, I agree with Matt. It started off spinning the way you'd expect it to, having thrown it up that way, but then it changed the way it was rotating.
Yeah, OK. Well, is that good observations, Hugh? I mean, what does that tell us?
Well, very good observations. What's happening here is that the book starts spinning exactly as you would like it to spin, but it turns out that spin about this particular axis is unstable in that it doesn't like to spin like that for very long. And so the book starts to tumble almost out of control, but then magically it starts spinning nicely again, but in the opposite way around. And so when you finally catch the book lands in your hands upside down.
Yeah, now this is all rather different to the two different ways of spinning that we saw earlier, which Matt and Tom tried. So, I mean, that was all very simple, wasn't it?
Yes, well, those two spin directions are what we would say stable. Now, you can imagine it's a bit like trying to holding a pencil by its tip. Now, if you try to hold the pencil hanging downwards, well, you could hold it like that for hours if you really like to, because gravity is pushing downwards and that direction is stable. But if you try and balance a pencil on your fingertip pointing upwards, well, that's unstable and it tends to fall down. Now, if you imagine the pencil on the tip of your finger, well, we can think of that like a pendulum, like a pendulum in an old grandfather clock, that when it's swinging down the bottom backwards and forwards, that's a stable situation. But if you imagine tipping that wooden pendulum right up around 180 degrees so it's pointing upwards, it wouldn't stay there for very long. In fact, it would swing down, it would go right the way around the bottom and back up to the top again. So the thing that happens with instabilities is that they quite often involve moving away from where you started and coming back again, but the other way. And then, in fact, the upside-down pendulum would then move away again and go back and come back to where it started again, but this time from the same way it started. And this is exactly what would happen with the book. If you toss the book up high enough, it will, in fact, do another flip and come back exactly the right way up again.
OK, now, of course, this doesn't just work for books. We were earlier talking about, when you throw your mobile phone in the air, we're going to find out what happens. So this is, I suppose, exactly what happens, because it's the same sort of shape, isn't it?
Exactly right. And the reason we didn't start off doing it with the mobile phone is that perhaps you at home might not have been quite too keen to try it. But now that you've seen it happen, I think you will find it's irresistible as you're walking down the street just not to toss your mobile phone up, and when you catch it, it comes back in your hand upside down.
Now, we're going to have started a craze across the eastern region, aren't we? But also, I mean, do kind of human beings, living things, do they ever kind of experience these kind of tumbling forces when they spin?
Yes, well, it's very interesting. In fact, there are no forces. That's, I guess, the point, that the book and the tennis racket and so on are tumbling through space with no forces causing them to spin at all. And a cat which falls out of a tree, it manages to use the same kinds of principles to move itself around.
OK, well, there we go. Thank you very much to Hugh Hunt for that explanation, and also to all of you, and to Norwich School. And we'll be back again next week with more science that you can do at home, hopefully. So until then, it's goodbye.
Thank you very much, guys. And on next week's Kitchen Science, Derek's going to be in Cambridgeshire with a big vat of liquid nitrogen at minus 200 degrees Celsius and some balloons. So needless to say, you won't be doing this one at home, but it's a great listen. So stand by for that next week. Amy, well done.
Thank you.
All right, you've won yourself our electronics kit. We thought you deserved it because you did the experiment. Well done.
All right,
Thanks for being an experimenter on The Naked Scientist.
Okay.
And with the teaser question, the answer is the stapes, which actually means in Latin stirrup, and it's in your ear. It's only 3.3 millimetres long. Amy in Histon, Duncan in Braintree, Deborah in Braintree, and Bill in Canada also got that wrong. But this week's winner is Sierra from South Jersey, and apparently South Jersey loves us, which is wonderful.
Thank you, South Jersey. Right, very quick question from Les. Hi, Les.
Hello, mate.
Fire away with your quick question.
The quick one is, how come I stay out the sun in the morning when I'm driving to work?
Yeah.
And I sneeze.
OK, well that, Les, is called the photic sneeze reflex, and it's something which is a big problem for people who want to be in the RAF or in the US Flying Corps, because when you get blinded by light, 1 in 4 people has this. It's thought to be genetic, and it tends to run in families. It seems to be that when you have bright light going into your eyes, in those people that are susceptible, then the light in some way triggers you to want to sneeze. We used to think it was because the light made eyes water, the tears ran down into the nose and tickled the nose, but it happens far too quickly for that, so we don't think that's true anymore. We think it's actually that there's a bit of miswiring in the back of the brain, and the eye blinking and pupil constricting centre in the back of the brain is at the same time triggers your sneezing centre. So when the two things happen, you want to sneeze. It's called the photic sneeze reflex. But thanks for joining us on The Naked Scientist. Well, that's pretty much it for this evening. So just remains for me to say thank you very much to Dave and Phil for doing an amazing job helping with tonight's programme. Our wonderful production team, Anna Lacey and Petro Minch, who do a brilliant job of putting this show together every single week and handling the massive numbers of phone calls, but especially to you at home for joining in. We couldn't do it without you. Next week we'll be talking all about the science of cancer. We'll be having Gerard Evan from the University of California, San Francisco, and Dr. Catani will be reporting from the National Cancer Research Institute conference with Fran Bulkwell. Have a good evening.